Hello everyone, in this video I'm going to present a TCST paper titled Energy Storage in Paraffin, a PDE Backstepping experiment. This is a joint work with our colleagues at UC San Diego, Mitsutoshi Makihata, Renkun Chen, Miroslav Kristik, and Alberto Pisano. Our motivation is driven by a recent high demand of the efficient thermal energy management owing to a recent advancement of sustainable and renewable energy. This pie chart shows the utilization ratio of the electricity consumption in the US residential sector in 2018. We can see that almost the right half of this pie chart is involved with thermal processes such as heating and cooling. There are mainly two types of the thermal energy storage systems. One is the sensible heat, which stores energy by temperature change, and the other one is the so-called latent heat, which stores energy by liquid-solid phase change. Such a latent heat energy storage systems are utilized for heat exchanger and spacecraft thermal management and so on. Among several materials, paraffin is the most representative organic material for latent heat storage system, which motivates our work on melting control of paraffin for enabling a desired energy storage system. We consider cylindrical shape of the paraffin, which is completely occupied by the liquid phase on the top region and the solid phase on the bottom region. For simplicity, we assume that the temperature profile and the interface position between liquid and solid phases are uniformly distributed over a cross-sectional area of the cylindrical shape, which enables us the approximation of the physical model in one-dimensional coordinate in vertical axis. There are two state variables. One is the temperature profile, and the other one is the liquid-solid interface position, denoted as S of T. As a temperature condition, the temperature at the interface position is always maintained at constant melting temperature, Tm. And moreover, we manipulate the heat flux Qc of T located at the top surface of the liquid phase. We consider a physics-based model of such a melting process known as the Stefan problem, which is given by a partial differential equation, PDE, of a temperature profile and ordinary differential equation of the interface dynamics. We can see that the PDE of the temperature profile is a kind of simple given by a heat equation in the entire spatial domain with two boundary conditions given by an energy balance and temperature condition. What makes unique this entire system lies in the dynamics of the ODE of the interface position, which is given by an energy balance. And this dynamics depends on the temperature gradient at the interface position. And actually, such a state-dependent moving boundary problem makes the entire system something called geometric nonlinearity, which renders a significant challenge for the control and estimation design. Here is the control problem we consider. We essentially manipulate the heat flux Qc of T so that the interface position is driven to our desired set point SR under the injection of the only positive heat input. That's the control objective we consider. We approach to this problem by the method of the energy shaping and backstepping. First, we derive a steady-state temperature profile and the heat input for a given set point position SR analytically. Then we introduce the potential energy of the system given by this formulation from physics perspective. And then we can see that this energy variable satisfies the energy conservation law, saying that the energy growth is equivalent to the gap between heat input and heat loss. We design QCT by energy shaping method so that the energy variable is shown to converge to a desired energy value at a given set point position, with further satisfying input constraint in the control problem we consider. Finally, we theoretically prove the stability of the closed loop system by the method of backstepping and Lyapunov method. And that's how we arrive at the theorem saying that Under the control law formulated by this equation, the closed loop system satisfies two properties. One is the constraints of the satisfaction of the constraints, and the other one is the global exponential stability in the spatial H1 norm, which implies the convergence of the interface position to a desired set point SR. So our objective is achieved with the proposed control design. This is a good starting point for control design, having a theoretical result. However, towards practical implementation, we need to further design state estimator under available measurements, because we actually cannot obtain an entire spatial profile of the temperature. And next, we need to approximate the spatial integration in the designed control law. And finally, we should design the digital system under the measurements and controller obtained at discrete sampling time. So we approach to these programs step by step. We design a state observer under available measurements of the interface position and surface temperature to obtain an estimated temperature profile to be used in the control input. We design an estimator by the system of the copy of the plan plus only one output error injection of the surface temperature at x equals 0. Actually, this estimator is a kind of simple because we didn't derive sophisticated observer gains. However, even with this estimator, the estimated temperature profile is shown to converge to a true temperature profile from Stefan model. And therefore, this design is sufficient for our control problem. Next, we introduce a model reduction of the designed PD observer to an OD observer so that the designed control can be implemented in practice. We introduce a reduced order state by evaluating the temperature, estimated temperature variable at finite number of grid points spaced uniformly for a given discretization number large n. Then, through finite difference approximation, we can derive an OD observer for the reduced order temperature state. And then, using this estimated variable on the applying the trapezoidal approximation in the spatial integration of the control input, we can derive the control design for a reduced order temperature state. Then we can see that the designed control input is a nonlinear function with respect to the measured value that owns the advanced property of the design procedure. Finally, we develop a digital system for the sample data design. The question lies in the fact that if the time step size delta t for computing the observer state is sufficiently smaller than the sampling time interval for the measured value, then how we should deal with it. Let's consider the case where the sampling time interval tau is triple the time step size delta t for computing the observer state. We utilize a method called intersample predictor developed by Paraffin and calibrate, which calculates the measurement update at each time step during sampling time period as an ISP state W of t. The measurement update equation is given by a rederivative of the measurement equation associated with the continuous time model. And that's how we derive a digital system for the control and the ISP-based observer design. Finally, the proposed control algorithm is implemented in the experiments of melting paraffin. The melting temperature of the paraffin is 37 Celsius degree. And we have two sensors, One is the thermocouple rotated at the top surface of the cylindrical paraffin, which detects the surface temperature. And the other one is the ruler attached next to the cylindrical paraffin to measure the liquid-solid interface visually. And our actuator is a Kapton heater, which is connected to a circuit board under the manipulation of the input current. And due to the device limitation, this input current has a constraint for the upper bound. However, by appropriately tuning the control gain, we can guarantee the satisfaction of this input constraint. Before implementing the proposed control algorithm, we first conduct an experiment with constant input for parameter calibration. First, we conduct open loop experiment under constant input IC equal Imax, maximum input current, for 2 hours. And the collect measured data at every 10 minutes in the experiment. Then, as a second step, we calibrate unknown parameters H and Q loss involved with heat loss for data validation of the estimator. Then we can see that in these two figures, the estimated value of the interface position and the surface temperature is sufficiently close to the measured data obtained at every 10 minutes. Using the calibrated parameters, we conducted experiment with proposed closed-loop control algorithm. We consider the set point position SR to be 2 cm and the sampling time interval tau to be 10 minutes. In the experiment, we set the initial input as Imax until interface reaches 0.5 cm and then start implementing the control algorithm. The left figure shows the plots of the interface position, and the right figure shows the visual image of the experiment. And from both figures, the interface position successfully converged to the set point position, and hence the experimental results were successful. Here I'm going to show the results of the input current on the left plot, and the surface temperature of the measured data and estimated value on the right plot. From left plot, we can see that the control input nicely converges to the steady state input calculated prior to the experiment. In the meanwhile, from right figure, we can observe that there is an error in the estimated value from the measured data, which is perhaps due to the error in the calibrated parameter through the open loop experiment. However, even then, we can see the sufficient robustness of the results of control the experiment. So this estimation error is actually reasonable, and our control is shown to be robust with respect to such a parameter error. Finally, I'm going to show the video of the experiment. Here, the set point position is depicted as white line, and once the experiment is started, we can see that the liquid phase is expanding from the top region and gradually converging to our desired set point SR, depicted as white line. As a summary, we have derived a nominal feedback control law for melting paraffin modeled by the Stefan problem by energy shaping backstepping method. And then we proposed an implementable control algorithm using state observer and model reduction and ISP-based sample data redesign. And finally, the effectiveness of the proposed control algorithm is validated in the experiments of melting paraffin in real time. This concludes my talk, and thank you for your attention.